Welcome to the third of 5 videos exploring the VCU-based design example for Avnet's UltraZed-EV Starter Kit. This design example enables hardware-accelerated processing of H.264 and H.265 video available in the EV family of Zynq UltraScale Plus MPSoC devices. In the second video in this series, we reviewed the Vivado design scripts for the design example and used these to generate our Vivado block design. This provides a great starting point to explore customizing your PL for your development effort. In this video, we're going to demonstrate an example GStreamer pipeline for VCU accelerated video decode and playback. We're going to cover how to discover and configure that DisplayPort interface from the command line. We're going to test the DisplayPort display with GStreamer's video test source element. We're going to review a pre-constructed GStreamer pipeline for hardware accelerated decode of a local video file, and we're going to demonstrate that decoding on a local DisplayPort monitor. So let me switch over here to my desktop. So here on the desktop, I've got an UltraZed-EV Starter Kit. It's connected to a 4K Samsung display with a DisplayPort cable. We've got Ethernet plugged in, which we're not actually going to use, a micro USB connector running to the PC for our serial connection and power. I'll highlight that even though this is a 4K display, you're going to see in the demo that it only supports 1920 by 1080, and that's because the DisplayPort itself on the I/O carrier card only has a single serial lane running to it. And at HBR2 high bitrate 2 mode for DisplayPort, that can only support up to 1920 by 1200 resolution at 60 frames a second. So I'm going to go ahead and turn the board on here and boot these images while we're talking a little bit more about the test documentation in the repository. So taking a look at the repository, under the porting folder, there's the RDF documentation testing, and 3 folders under here for DisplayPort, RTP streaming, and USB webcam. Now you can take a look at these documents kind of in the raw, or what I recommend is going over to the project release page if you're browsing the repository online. And inside of the release notes, there is a link to some additional getting started instructions which organize all of those test documents kind of in a logical flow. So we're going to click on this link, instructions used to validate the operation of this design. And that's going to take us here to testing the design with the UltraZed-EV Salmon carrier card. So there's 4 sections: working with a DisplayPort display, working with the VCU decoder, working with the USB webcam, and the VCU encoder demo for doing DisplayPort display and network streaming of encoded video. So in this video, we're going to work through these first 2 sections, learning how to use the DisplayPort, testing it, and then doing a video decode and playback. I already have these documents open on these subsequent tabs, so let's dive right in here and take a look at how we configure the DisplayPort interface. So we're not going to step through all of these commands, but you can step through this logically. This walks through kind of exploring how you tell what devices are available in your system for the DisplayPort. So it shows up as DRI card 0, how you find out more information about that device, finally going and exploring the device a little further in the debug file system, and then looking to see what the device name that's given to that device by the system. So right here, this is going to be important for the next step, and this device name is going to allow us to explore the capabilities of this from the command line using the mode test command. So I'm going to switch over real quick to my TerraTerm window. The system is done booting, and we're going to use mode test to dump the capabilities of that display connection. So first you'll see at the top of the output, we're dumping the display connection, and this is the mode table that the display supports. So 1920 by 1080 all the way down to 720 by 400. We've got the EDID blob, some other parameters. You'll notice here that the CRTC is configured for 1920 by 1080, 60 Hertz refresh. And if I switch back here out of full screen mode, you'll see that there's actually a boot console being displayed on here. 2 other things to highlight coming out of mode test. There are 2 configured planes. So plane ID 34 shows you the data formats that's supported. The type of plane, value 0, is an overlay. So plane 34 is the overlay plane. Plane 35 is the primary display plane. And you'll see the overlay plane supports test pattern generation. The primary plane has alpha blending parameters that you can configure, and we will use those shortly here in the demo. So the next step in testing the display is going through the release notes. We're going to learn more about alpha blending. And so that's what these two parameters here. Configure alpha blending to if you want to blend the two planes, or you can just turn alpha blending off so you only display one plane. So the next step in the documentation is going to take us to the video test source example. And I'll highlight here in the documentation that here is the GStreamer pipeline that we're going to demonstrate. So it takes the video test source element, which is a software generated test pattern. It's going to stuff it into a queue element, which is just a buffer in memory. And then that is going to pump data out to KMS sync, which is kind of the kernel mode subsystem for displays. And that's how data gets in and out of a GStreamer pipeline out to a display device. So the pipeline that is built in this example, that's what the elements that it uses. And I want to highlight here that these pipelines use the fake sync element to kind of prototype the pipeline in stages. So we add an element, we test it to make sure that we've got all the parameters correct, then we add the next. And that's a great way if you start with a demo pipeline, you try to run it, maybe you're pasting a command you find on a wiki or on documentation somewhere and it doesn't work. If you step back through that pipeline using the fake sync at each stage, you can find out where the pipeline's breaking, and that helps you sort of debug what the issue is that's causing your pipeline to fail. So let's take a look at the video test source element using GST inspect. So there's a lot of information popping out here. What I want to scroll back and highlight here is one of the parameters of the video test source element is you select a pattern to generate. So in this example, we're going to generate the SMPTE color bars on the display. You can choose any one of these. And there's some other parameters here we're not going to use, but if you want to explore those, you can do that too. Take a highlight here. So if we just do a GST launch with the test pattern and send it to fake sync, it shows you that the pipeline runs, but nothing will actually come out to the display because we haven't gotten that far. And then if you scroll down through here, we build the rest of the pipeline with those three elements. And I'm just going to jump straight in, and we're going to do a video test source. XRAW 720p 15 frames a second, and we're going to send it to that display device here that we discovered kind of at the beginning when we were looking at the DisplayPort. And then because the display is set for 1920 by 1080 resolution, we're going to set this parameter full screen overlay equals true. And what that's going to do in the background, it's going to change the display mode of the display so it's running at 720p and put this test pattern out there. I'm going to switch back to our kind of shared desktop here. We're going to run this pipeline, and you'll see we have color bars. Now, one of the crazy things about this is that the color bars look all washed out. You really can't see the colors. And this is an artifact of the webcam that I'm using to record this. So what we're going to do really quick, I'm going to go and reduce the exposure in the camera controls on my webcam. Just a couple of settings. You'll see the color bars will come into focus here. The rest of the background gets dark, but you'll see the colors really pop out here on the color bars on the display. And we're going to leave the webcam configured like this for the rest of the video. So you can distinguish here in the webcam, you can distinguish between the cyans and the purples, the dark purple here kind of in the middle, and then on the left-hand bottom left corner is more of a navy blue. So it's a fairly accurate, or a little bit better representation than that washed out image we started with. All right, so now that we have the color bars working and the color looks pretty accurate, I want to show you what it takes to go and generate this. So we're going to put this pipeline in the background so it continues to run. And then I'm going to use the top command to show you the CPU utilization here. Let's take a quick look at this full screen. So up here in the CPU percentage, you can see the GST launch command has taken about 27% of one of the single CPU cores to generate this test pattern at 720p 15 frames a second. So it's not a heavy lifting, but you know, it does take some processor cycles to go generate this, so it doesn't come for free. We'll just keep that in the back of our mind. So cancel this, and we're going to close out this test pattern. So what I want to do now that we've seen that at 720p 15 frames a second, that takes about 27% of a CPU. we're going to go and run the same, we're going to go and run that same test pattern at 1920 by 1080. Now, before we do anything else, I'm going to go ahead and try running this at 1920 by 1080. Now, the display is already configured for 1920 1080, so we don't have to use the full screen overlay to change the mode. But I'm going to go ahead and run this. You'll see that the pipeline runs. There are no errors, but there's nothing out here on the display. I'm actually going to cancel the pipeline, and what we're going to do is we're going to go back in here and look at the mode test command. So we have our two planes. We've got our overlay plane, and then we've got our primary plane. And right now, the primary plane has alpha blending turned on, and the value is set at 255. So with a native resolution pipeline, what you need to do is you either need to turn alpha blending off or set it so that it's actually disabling blending with the alpha parameter. So I'm going to go back here and I'm going to turn this pipeline back on. We don't see anything on the display, and I'm going to put this in the background so that we're displaying the pattern, but you're not actually seeing it. And we're going to go and explore these alpha blending parameters. So if you recall, the alpha setting was set to 255. What I'm going to do is turn alpha blending off for the primary plane. We're going to set at the display the parameter on plane 35 alpha to 0. And now we have our color bar test pattern back. So something you can do, we know when I set this back to 255, it brings back the serial console. So let's set it somewhere here in the middle, like 150. You're going to see it's actually blending both of those planes now. So I'll expand the webcam here. You can see we're blending both the console and the color bar test pattern. So both of those planes are actively being written in the background, but we're using the alpha blending capability of the GPU to go and blend those two planes. So I'm going to restore this back to its original setting so that we can't see this. What we want to do is we actually want to turn alpha blending off for this. So in order to do that, we're going to use that other parameter. Let me bring that back up here just to show you down here. So we set the alpha value. What we really want to do is we're going to turn G alpha enable off. I'm going to copy and paste from my little buffer here this command to turn alpha blending off. And now alpha blending is turned off and we've got our test pattern back. So this is running 1920 by 1080. Looks pretty similar to the one we saw before because it's full screen. What's going to be a little bit different is the CPU utilization. So before we were generating a 720p test pattern, now we're generating a 1080p test pattern. And you'll see here that it jumped from 27% to 61% of a CPU. And that's just one of the CPU cores, one of the Cortex-A cores that's generating this test pattern at 15 frames a second, 1080p. All right, so now that we've validated that we can get a test pattern out on the display and our colors look really good, what we're going to do next is we're going to jump right into decoding. So we've already highlighted here in the release notes the alpha blending documentation. So we're going to step right down here and test video decoding. And the same thing is true here. So let me cancel our test display. Over here in the test documentation, let's start by taking a look at the complete demo pipeline. So we're going to start with a video file input. And we're going to bring that video file in through the file source element into a demuxer. So a video file is typically racked in a container format because you've got one or more video streams as well as audio tracks. So you need to, before you process the video, you need to split those audio and video into two separate paths. So that's what the demux element does. It parses the MP4 container, splits out the video and the audio. Now you'll notice here in this pipeline that there is an audio path, and I've just included this in the documentation for completeness. We're not actually processing audio in this example. We're just discarding the audio, but we're focused on the video path. So you demultiplex those two into a video and audio stream, and then you have to send the video stream through an H.264 parser, which takes the H.264 video stream format and then presents that, it reorganizes that and orders the data as frames to send over for decompression to the decoder. Then we insert our decoder element. We're going to queue the data, the raw data coming out that's decompressed from the decoder, and then we're going to send that out to the DisplayPort through KMS Sync. And like the other documents in this test documentation, this will step through, including actually downloading onto the target the demo video, the Big Buck Bunny trailer we're going to demo today. But it steps through and it builds the pipeline from scratch, shows you how to explore all the elements, how to use fake sync to systematically build up a demonstration pipeline. You inspect the file source element. You can make sure that you can bring in the file first, and everything works there before you go and start adding the demuxs. And you can step through stage by stage and build the pipeline. So what we're actually going to do here is we're going to go ahead and just take a look and see the Omx decoders that are available. So Omx is OpenMax, and you'll see here on the platform that we've got an H.265 encoder decoder, an H.264 encoder decoder using the GST inspect command. And these are our windows into the VCU hardware accelerator. So these are the GStreamer elements that actually send data and pull data out of the VCU hardware acceleration block in the UltraScale Plus MPSoC. So for this demonstration, we're going to do an H.264 file decode. So let's take a look at the decoder element and scroll up here. So this is the OpenMax decoder for the Zinc UltraScale device. This is your sync pad is going to be the input into the decoder. So we're going to have an aligned stream format, byte stream coming in at a specific height and width. And then the source is going to be the output of the decoder into the rest of the pipeline. And that can go to GL memory as RGBA data, or that can go just out as raw with a height and frame and a frame rate. And then down here, the element has certain properties that you can configure. And so when you use the GST inspect command, that'll expose to you all of the properties that an element can use. And you'll look here that there's settings for internal entropy buffers and latency mode. And this is a good time to go and highlight that. Let me step back out here to the desktop. In Xilinx Product Guide 252 for the VCU, the Logic Core IP Products Guide, there's documentation on the video codec unit. And if we jump to page 128 of this document, you will see here in table 12.6 that these GStreamer decoding parameters are actually documented for the decoder element that Xilinx provides. So you can read in here and learn about what the entropy buffer setting does, what the recommended values are, and the same with low latency mode. And you can learn additional stuff about the decoder and encoder in this document as well. But I just wanted to highlight that's how that ties in here to the GStreamer element settings for internal entropy buffers and latency mode. It's actually documented by Xilinx in the product guide. So let me go back here to our Terra term window. And I want to highlight again that we had turned off alpha blending. So that's why this pipeline is going to work. I'm going to copy and paste the complete pipeline for our video decode. And we're going to hop over here and see that we're actually doing a video decode on the display. So let me make this full screen for a moment. You can see, so the webcam is recording at 1080p 30. The display itself is running at 1080p 60, and the source video is 1080p 30. So this should look nice and smooth on the video, which it does. We've already adjusted our camera exposure so that the color representation is pretty close. And you can see this is pretty smooth. So it's chugging along, decoding and displaying 1080p video. Now I'm going to hop back to a Terra term for a moment, and we're going to put this in the background and take a look at what the processor is doing while this video decode is going on. So let's let this refresh here a time or two. And I want you to look here at the top of this list. And you'll see that GST launch is taking a little over 2% of one CPU core. So if you remember in our 720p video test pattern the processor was generating, that took 27%. When we bumped that up to 1080p, that took 60 plus percent. Now that we're doing a hardware video decode of 1080p 30, it's only using, this processor is only involved 2% of the time for one core. So I'm going to go back here to the full screen, and you can see it's chugging along 2% of the CPU. So it's basically just managing some buffers and DMA. It's not really doing a whole lot, separating out the video stream and setting that up to go to the VCU and then right out to the display. So the data path is pretty clean. It's pretty efficient. And the video decoding itself looks pretty good. So that concludes this video. You go ahead and close this out. Hopefully this overview of working with the DisplayPort and the VCU accelerated decoder helps you get started evaluating the platform for your own project. If you continue in the video series, the next video is going to help you learn more about working with a USB webcam as an input video source, after which in the final video we're going to use that webcam to test the VCU encoder capability and stream that out over a network, kind of show you a complete end-to-end demonstration. So thank you for listening.